as I announced in the previous class, and for the 2 weeks, I will provide only online classes because uh, actually the college will have so currently the college is having the midterm period for 2 weeks. So and then due to the COVID-19, so the university need to provide enough rooms for students during the exam period. So which means that the university does not have enough classrooms during the exam period. So we need to provide only the online classes. I hope everyone is on Zoom now. 2023. Okay. Let's start today's class. So and then before starting the class, and then someone sent me an email about some lab assignment. So actually, the most of the students, the issues are related to the license issues of the Questa. So actually, when we tested the Questa simulator on on my computer also, we tested the Questa on TS computers also, but it worked well. So I think the the license issues are maybe caused by some students' own machine. So if you encounter some license issues, then you can visit the TAs. Okay, you can stop by TAs and then with your laptop computers. Then TAs I hope TAs can help the students. Okay. Okay. So let's start today's class. So in the previous, what do you mean? What is review guide? What does that mean? What? What review? So and then actually, as I mentioned during the class, the exam questions will be very similar to the homework questions. Okay. Now, so if you can simulate the system variable with the other tools, then it's okay. So you can use other tools. Okay. So okay, let's start today's class. And then also I will post some exam logistics on the Blackboard soon. Okay. So, okay, let's get started. So in the previous class, we learned about the data path element. So you can just understand that data path elements are hardware components. So like the registers, ALUs, and then multiplexers. So those hardware components just process digital signals. So actually, you can understand that data path elements are hardware components that process digital signals, and that's it. So actually, we can build the single cycle processes using data path elements. So actually, I also explain how instructions are executed in computer processors. So, we require 5 steps called instruction fetch, instruction decoding, execution, memory, and write back. So which means that the hardware components need to perform the required operations for these 5 steps. Okay. So in the previous class, I explained how we can build some hardware data path elements, and then how to connect each how to connect the elements using the wires for supporting the required operations for 5 steps. Okay. Also, I explained some behavior model of the data path element. So actually, the task for the second design lab is to build the data path element using system Verilog. So I think so this this will be helpful for the students. Okay, so I explained how to build each data path element. Also, I explained until the branch instructions. So, and then, okay. So, actually, in the chapter 4, so in chapter 4, we are learning about some hardware process architecture. So actually, our processor will support some several RISC-V elements, but we can categorize these instructions like the instructions that access register file and memory, and then instructions that access program counter. Okay, so what kind of instructions access register file or memory? Actually, most of the instructions. Okay, so most of the instructions except the control instructions access register file or memory. Like, so you can say that the arithmetic instructions or the memory instructions, like load and store instructions, handle register file and memory. So which means that these instructions update data on registers or memory. Okay. And then how about the control instructions? Oops. Okay. How about the control instructions? So actually, control instructions update program counter. Okay. The control instructions. So control instructions include branch instructions or jump instructions. Okay. So these instructions just change program counter. Then I already explained about the branch data path for the branch instructions here. So actually for this single cycle processor, the BQ is only supported. BQ is the only supported control instruction. Okay, so I will take an example of this BQ instruction. So BQ instruction is operand from register file. So BQ needs to read data from register file, and then as I mentioned, these two data in two registers are compared each other, and then we check the equality of these two data. Then if the equality is, if the result is true, which means that two data are equal each other. So which means that PCE is update to the target of the branch instruction. So in order to support these operation, I also explained some data path elements and connections for branch instructions here. Okay. And then how about the archive and other instructions, like the archive instructions and the memory instructions? So I already mentioned that these instructions update data on registers or memory. So So let's see those on how these instructions are executed in our single cycle processor hardware. Okay, so we can think like so I will take the example of the add instruction, like add x1, x2, x3. So when the add instruction is executed, then which port is activated? This port and this port. The source register number. Source register numbers are given to registers. Okay, so actually the register numbers are extracted from an instruction. Okay, because encoded instructions include these register numbers. So register numbers are given to the read register 1 and read register 2 of the register file. Then after some delay, because the register is a hardware component, and then so every hardware component has delay. Okay, so after some time, after some delay, then we can read the data in these source registers. Okay, so data is given to the ALU. So also the read data 2 is read from registers. So you can find that it's a box because we require box in order to support I-type instruction. Okay, so this add instruction requires the two register operands. So we select this path. So if you see this mux, then you can find that when this mux selection signal is 0, then this path is selected. Otherwise, another path is selected. So for this add instruction, so add instruction is the R-type instruction. So we can know that we need to select this path, right? So which means that ALU source should be ALU source should be 0. Okay, for the R-type instruction. So operands are given to the ALU, then result is generated. But we know that this result should be returned back to the registers. Okay, then so if you see the output of this ALU, then we can find that the output port of the ALU is connected to the address input of the data memory. Also, this path is connected to the box after this data memory. So which means that the result is delivered to this box, also delivered to the address of data memory. So for the R-type instruction, and then if you see the output of this multiplexer as a box, then we can find that the output of the box is connected to the port, write data port of the register file. Okay? And then this data will be written back to the register with the write register numbers. Okay, indexed by write register number. Then, so which path should be selected for this multiplexer? It's easy. So which means that this multiplexer receives two inputs from data memory output, so read data. Also, this multiplexer receives another input from the ALU result. So it's the result from ALU. For this add instruction, so add instruction, actually for this add instruction, the add operation is performed by ALU, so which means that we need to use the result from ALU, right? Understand? So which means that so for this selection signal, for this mux, we need to set the mem to reg as the 0, right? So we need to select this path. So which means that the result of ALU is connected to until write data port. Okay. So the required operations for this add instruction are implemented in this data path of the single cycle processor. Then let's see another example. How about the load instruction? Like, so let's take another example of the load instruction, like load x1. So is offset. So actually this is immediate value. So x2. So if you see that this load instruction, then we can say that, oh, this load instruction is the I type data. So which means that I type data includes one source register and one immediate data. So this is the RS1, the source register 1. So this register number is given to the read register 1 port of the register file. Then also after delta T delay of the register. So we can we can get data from this register file. Okay. And how about the immediate data? So if you see that this instruction, we cannot find any RS2 number. So source register 2 number. So so which means that actually the garbage data, the garbage number will be delivered to the read register 2. And then, so you know, the register is also the kind of combination logic. So which means that if the register number is given to the register file, then register file generate the output stored in this register. Okay. What does that mean? Okay. So okay. I explain about that. So one student asked the question, but it's related to store instruction, not load instruction. I also explain about the store instruction. Okay. So garbage data is given to the read register number 2, and then that means that the garbage data will be generated from this read data 2 port. But we will use the immediate number, so immediate data included in this load instruction. So which means that the immediate field is given to the immediate generator, and then immediate generator 64-bit number. So this is because ALU receives 64-bit data. Okay, so we apply the sign extension for this immediate data. Okay, so if you see this mux, then you can find that this mux received the one input from the read data 2, also another input from the immediate generator. Then we need to select this path, right? Okay, because load instruction use immediate data. So which means that ALU source should be 1. Okay, because we need to select this path. So the immediate data is given to the ALU. Also, this read data 1 is given to the another input of the ALU. So in this ALU, the add operation is performed because we need to generate the address like the immediate plus x2. Okay. So output of this ALU is given to the address port of the data memory. So also this address, the result will be also given to delivered to the another input of this multiplexer. But this is the load instruction, which means that we need to access the data memory with the generated address, right? So we get data from this data memory indexed by this address. Then, so we need to select the which path? We need to select this path. So, which means that output from data memory. Okay. So for the load instruction, mem to lag should be 1. Okay. So this path is only selected, and then this path is given to the right data. So, and then the x1 is the destination register number, and then this x1 is given to the right register. Okay. So that's how the load instruction is performed in this single cycle processor hardware. Okay. Okay. Let's see another example. Store instruction, like store x1 immediate x2. So delete this part. So how about the store instruction? The definition of the store instruction that we need to calculate the address for store instruction from this part, and then also store instruction need to read data. Okay. So in the store instruction, this is the RS1 and then this is the RS2, right? So if you check the S-type instruction of the RISC-V, then you can find that for the store instruction, so S-type instruction, this register is the source register number 2, and then this register is the source register number 1. Okay. So which means that so for this register number is given to the read register 1 port of the register file. Now how about this RS2? So RS2 of the store instruction is delivered to the read register 2. And then also the store instruction requires immediate data in order to generate the address of the store instruction. So immediate data is also given to the immediate generator. So which means that this immediate data is expanded, so it becomes the 64-bit data. And then like the load instruction, this is the RS1. So the data for RS1 is given to the ALU, and then immediate data is given to the also ALU, then address is generated. Then how about this one? With the source register 2, then we can read data from the register file. So this data is delivered to the right data port of the data memory, because the definition of the store instruction is that the data in register 5 is transferred to the data memory. So which means that we need to write data to the data memory, right? So for this store instruction, ALU source should be also 1, because we do not use this data for this address generation, and then we use this read data, output of the read data 2 for the input data for data memory for store instruction. Okay, and then store instruction does not require write back process. Okay, data is returned to the data memory. Okay, and that's it. Understand? Okay, this figure shows the full data path of the single cycle processor. So firstly, we start from the individual data path elements such as the instruction memory and then program counter register and then register 5, ALU and data memory. So we first define the operations of these data path element. And then, so input and output ports of data path element are connected each other. Okay. And then by connecting the input and output port of this data path element, then we can implement the required operations for executing instructions. Okay. And then as I already explained, this path is for the control instructions because the PC is updated. Also, this path is the path for other type instructions or memory instructions. Okay, and that's it. So we build a processor, but something is missing in this process architecture. What is it? So what is missing? Yeah, right. That's right. So, so we cannot find any clock signals, but the clock signal is the very basic signal. So we assume that the clock signals are already given to this single cycle processor. Okay, it's a good observation. So we need the clock, and then some what is missing? Another point. Yeah, control instruction. We input. So actually, I already explained how the control instructions are executed in this single cycle processor. So I explained how the BQ is executed in this processor. So the missing part is not control instruction. This missing part is control signals. Okay. So if you see this figure, then we can find that input and output ports of data path element are connected. But we can find, but in this figure, we can find several control signal port. Okay, so like ALU source, left, right, ALU operation, mem right, and so actually these are ports for control signals. Okay, but in this figure, control signals are not connected, so it's open. Okay, so then the first we define the data path elements in this single cycle processor, and then we need to define control signals. Okay, so which means that we need to implement controllers. Okay, controller. Okay, so what is different? So if you see that this single cycle processor architecture, then we can find that there is a control unit. So, and then you can find that the control port of data path elements are connected to the output of control unit. So this is called the control unit, or we can call it as the CU because it's a control unit. So which means that in order to make this single cycle processor work properly, then we need to make a control unit, and then this control unit generate control signals for data path element. So what does that mean? So if you see this figure, then we can find that. So these are control signals like left, right, ALU source, ALU operation, PC source, blah, blah, blah. So these are control ports of the data path element. So which means that we need to generate control signals. So proper control signals for executing instruction. But I already explained in this previous slide. So which means that, so for example, for the store instruction, so I mentioned that, oh, ALU source should be 1 because we select this path for the another input of ALU. Also, I explained about the mem to reg signal for other instructions like load instructions or R type instructions. So which means that we need to generate control signals based on instructions, the type of instructions. Okay. So in the previous so in this slide, I mentioned that for the R type instruction, ALU source should be 0, and then mem to write, mem to read should be 1. For the load instruction, ALU source should be 1, and the mem to read should be, oh, this is 0, 1, something like that. So which means that these control signals are determined by instructions. Okay, so based on the instruction, we can generate required control signals. Okay, and then these control signals are generated from control unit. Then we can define the control signals. Also, let's start from the ALU control. So if you see the this ALU, then we can find that ALU received the ALU operation control signal. Okay, it is because ALU need to support the various operations by instructions. Okay, so ALU support various operations by instructions, and then ALU operations are decided by which signal? ALU operation signal. Okay, ALU operation control signal. So which means that we need to define this control signal. And then which means, so we can categorize the required operations for ALU by instruction. So for example, if load or store instructions are executed, then the ALU need to perform add operation, right? So when I explain about this R-type data path, R-type or load store data path, then I explained that ALU is used for generating addresses. And then in order to generate the address, we need to perform the source register 1 plus immediate value. Okay, so this is the add operation. So which means that add operation is performed by ALU. Right. So we require add operation. Then how about the branch instruction? We just support the PQ in this example. So in order to support the, actually in order to check equality of two data, then we need to perform subtraction. Okay, like A minus B. Right. So which means that ALU need to perform subtraction operation. Okay. And how about the R-type instruction? So in the chapter 4, we assume that our processor supports only 4 different R-type instructions like logical AND, logical OR, add, or subtract instructions. So which means that the required operations for ALU is determined by different instruction, different R-type instruction. So which means that if the instruction is logical AND instruction, then ALU need to perform AND operation, right? So it's OR, then ALU need to perform OR operation, and blah blah blah. Then we can define these control signals of the ALU control signal for different R-type instructions, like here. Which means that if in order to support the logical AND instruction, the ALU need to perform AND operation, then we can set the ALU operation signal as the 0, 0, 0, 0, and then 0, 0, 0, 1. Okay. So we can define some ALU control signals like this. Okay. So we first classify instructions, and then based on this classification, then we define the operations by ALU. Okay. So, but in this example of the chapter 4 single cycle processor, then we first define the 2-bit ALU OP signal based on the classes of instructions, and then we define the ALU control signal finally. And then this ALU control signal is connected to the ALU as the control signal. So this is because, so actually, so if you see this Excel sheet, then we can find that this Excel sheet shows the list of IV32I instructions. Okay, but you know that there are many other instructions in the IV32I. But in the chapter 4, we just support the several instructions, actually 4 R-type instructions, and then 2 memory instructions, and then 1 control instruction. Okay, but in reality, the RISC-V need to support many other instructions. So in order to support these many instructions, then ALU actually needs to have 4 bits. So with the 4-bit control signals, we can define 16 different operations by ALU, right? So, but you know, our ALU of this chapter 4 just to support 4 different operations, right? So AND, OR, add, subtract operations, which means that we just require only 2 bits for supporting 4 different operations. But actually, the RISC-V ALU need to support many instructions, like as shown in this slide. So we assume that ALU has 4-bit control signals. Okay, and then if you see this Excel sheet, then you can find that we can find the various categories of instructions like load, store, and shift, and arithmetic instructions, and so on. So actually, which means that also based on the categories of instruction, then the operation of the ALU can be also changed. So that's why we just define the ALU OP control signal. So, and then ALU OP control signal is determined by categories of RISC-V instructions. Okay. So it's a little bit as complex, but actually our ALU just to support the 4 different operations. So it's okay with the only 2-bit control signals, but in real RISC-V processor, actually the RISC-V ALU needs to support different operations. So so actually in chapter 4, so I explained the ALU operation is very similar to the ALU control signals of real RISC-V processor. Okay, So based on the categories of the instruction, the first 2-bit ALU OP control signals are determined. Okay. So if you see that this OP code field, then you can distinguish the different categories of instructions. And then also you can see that this example. So for the load instruction, the OP code is 000011, okay, here. And then for the store instructions, OP codes are different here, but these are memory instructions. So which means that, so if you see that this table, then we can find that OP code fields for load and store instructions are different, but these are memory instructions. So we can say that, oh, load and store instructions are memory instruction, and then ALU OP is the 00. So which means that ALU is used for generating addresses, okay, for the memory instructions. So the first ALU OP control signal is determined based on the OP code field. Okay. How about the BQ? So BQ is the branch instruction. Okay. And then if you see that this slide, so you can find, oh, for the branch instruction, OP code field is actually the same. So 011000011. Okay. Oops. Like here. So based on the categories of the instruction, the OP code has its unique field. Okay. For the BQ instruction, it's the branch, actually branch type. So OP code field is the 11000011. So, and then for this branch instructions, ALU needs to perform subtraction. Okay, and then ALU OP is defined as the 01. So which means that, so ALU is working for branch instructions. Okay. So if you see that another branch instruction, like then we can find that different branch instructions like BQ, BME, BLT, and BGE. But you know, these instructions require only subtractions because we just compare the equality or compare the magnitude of the two data. Okay, and then we need the subtraction. Okay, and then for the R-type instruction, the OP code field is the 0110011. Okay, and then we set the ALU OP control signal as the 10. So which means that this is the R-type instruction. So also if you see that this IV32I this instruction list, you can find shift instructions, arithmetic instructions, and the logical instructions are kind of arithmetic or logical instructions. But we can find that there are R-type instructions for this arithmetic or logical instruction. Also, we can find I-type instruction, such as the add instruction and add I instruction. So this is the R-type instruction that performs the add operation, and the add I is the I-type instruction that performs add operation. Okay. So if you see that this type of instructions, we can find the different OP code field like 0110011 for the I-type instruction, and then 0010011 for the I-type instruction. Okay, understand? So actually, our processor just supports the R-type instruction only. Okay, so which means that if the OP code field is the 0110011, then this, which means that, oh, this is the R-type instruction, and then ALU needs to support the various operations based on different R-type instructions. Okay, so first, the ALU OP control signal is set as the 1-0, so which means that ALU needs to support the supports the R-type instructions. Okay, and then based on this function 3 field or function 7 field, we can define the different kind of instructions. So based on this function 3 or function 7 field of the R-type instruction, then we can define the required operations for ALU. Okay, so ALU control signals are defined by different kinds of R-type instructions. Okay. Oh, it's a very good question. Okay, so we can distinguish the different categories of instruction with the opcode field. But you know, the opcode field is the size of the opcode field is the 7 bits. So actually, which means that we can define actually very large number of different categories of instructions. But ALU is only supports some specific operations like the memory instructions or branch instructions or R-type instructions. So, which means that ALU just want to know some specific operations. So which means that specific category of instructions. Okay. So we just set the first define the 2 bits of ALU OP signal. No. This. So another example is another question. So if you see this field, so you can. This is just ALU OP control signal, not the instruction data. So if you see this table, the function 7 field is occupies the instruction pin number 31 to instruction pin number 25. So actually these function 7 fields are included in an instruction. So we can find the function 3 field in an instruction, but this is different. Okay, not ALUOP. This is the ALUOP1 and ALUOP2 is just control signals. ALUOP control signals are not included in the instruction. Okay. Okay, so actually, if you see this slide, so actually, if the OP code fields are rows and stores, then we can ALU just performs add operation, and then ALU does not consider does not check the function 3 field for this case. But if the OP code fields are R-type instructions or arithmetic I-type instructions, then ALU needs to check the function 3 or function 7 field. Okay, and then this slide shows this requirement. Okay, so in order to distinguish different R-type instructions like add, subtract, and or OR instructions, then we need to check the function 7 field or function 3 field of the RISC-V instruction. Okay, and then based on this function 7 or function 3 field, ALU operation control signals are defined. Okay. So ALU control signals are a little bit tricky because ALU needs to support different kinds of instructions. Okay. These ALU operations are determined by different instruction categories, and then also different instructions in the same categories, like R type or I type instructions. Okay, but if you see that this summarized instruction list of the RISC-V, then we can easily recognize the required operations for ALU. Okay, so actually the so which means that in summary, we can check the OP code field and then function 3 field and then function 7 field of in an instruction. Then we can decide operations by ALU. And then which means that based on the OP code fields and then function 3 fields and then function 7 fields in an instruction, we can set the ALU control signal. Okay. Okay. I hope everyone can understand. So, so this slide shows the single cycle processor hardware architecture, including control unit. So if you see that this control unit, then you can find that control unit generates these control signals. But if you see that this control signals, then you can find that there is ALU OP. So actually this is the 2-bit control signal, so 1 down to 0. So which means that, so in the previous slide, we defined the ALU OP control signal here, so 2-bit control signals. So which means the first is the control unit generate the 2-bit ALU OP control signal. Okay, and then this ALU OP signal is connected to the ALU control, and then based on the some other fields like a function 3 or function 7 field, ALU control signal is generated. ALU operation. Okay. So also, if you see that this control unit, you can find this control unit received the instruction be field 0 down to 0. So which means this is P code. Okay. So what does that mean? The first we first check OP code field of an instruction, and then we generate the 2-bit ALU OP signal, and then this ALU OP signal decides, this is the memory instruction, or this is the branch instruction, or this is the other R-type instructions. And then we know that if ALU OP is 0, 0, then ALU need to perform add. And then 0, 1, ALU need to perform subtraction. And the 1, 0, ALU need to support various operations based on the functions 3 or function 7 field. So if you see that this ALU control unit, so this is another control unit for ALU, then you can find that this ALU control received the function 3 field and function 7 field. Okay, so then ALU control signal decides the ALU operation. Okay. So let's see another control signals here. So if you see that this control unit, then we can find that other control signals are generated from this control unit. But this control unit just receives bit number 6 down to bit number 0 of an instruction. Then this is the OP code of one instruction. What does that mean? If we just check the OP code field of an instruction, then we can generate the required control signals for data path, like branch, mem read, mem to read. So these control signals can be generated by checking the opcode field. Okay, understand? So, okay, so I explained how to generate the ALU control signal by control units and then ALU control unit. And then now I will explain how to generate the other control signals based on the instruction. Okay. So R-type instruction. So in our single cycle processor, we can know, oh, this instruction is an R-type instruction by checking opcode field. So which means that if the opcode is, what is opcode? Zero one one zero zero one one. So by checking this opcode field, so we can know that, oh, this current instruction is R-type instruction. And then, this control unit just received the pin number 6 down to pin number 0 of an instruction, like opcode, which means that we can generate the other control signals based on this opcode. So, okay, so R-type instruction. How about the branch control signal? So if you see that this branch control signal, so branch control signal is connected to one input of this AND gate. Then if you see that this AND gate, so this AND gate is connected to the 0 port. What does that mean? 0 becomes 1 if the two input data of the ALU is equal. Right. So if you see the output of this AND gate, then we can find that this AND gate decides the selection signal of this MUX. And then if you see that this MUX, then if this selection signal is 1, then this path is activated. What does that mean? So if this selection signal is 1, then we can select the target of the branch. So this branch control signal becomes, actually decides the enable of this AND gate, so which means it is required for branch instruction only, right? What does that mean? For the R-type instruction, the branch should be zero, right? Yeah, right. 0. So if the branch control signal is 0, then it becomes 0. Then output of this AND gate is always 0, which means that only this path is selected. So if you see this path, then you can find that, oh, this is the PC underbar curl, is the current pitch, and then this signal is the PC curl plus 4 because it's the adder. So which means that this signal becomes the PC underbar curl plus 4. So which is the PC underbar next. It's the next PC. Okay. So for the R-type instruction, the next PC is the current PC plus 4 because it's not a branch instruction. So which means that branch should be 0. How about the mem read? It's very simple. R-type instruction does not access memory, data memory actually. So we don't need to read data from the data memory. So mem read is 0. Then how about the mem to read? So we need, select this path I already explained for the alt type instruction. So which means that this should be 0 also. So this signal is connected to the selection port of this multiplexer. And then, this signal control signal should be 0 for alt type instruction. ALOP. So 1, 0, we already learned. How about the mem write? It's not store instruction. So it's also 0. How about the ALU source? The ALU source is connected to the selection port of this multiplexer, but we need this path. So ALU needs to receive another data from the register file. So ALU source should be also 0. How about the leg write? How about the leg write? Yeah, it should be 1, right? Because the alt type instruction is executed, then the result of alt type instruction is written back to the register file. So we need to perform register write. So it should be 1. So which means that if we know the category of instructions with the OP code field, then we can easily generate control signals, right? And how about the load instruction? So for the load instruction, OP code field is, so let's check, 0000011. So it's 0000011. So which means that if the OP code field is 0000011, then we can know that, oh, this instruction is a load instruction. How about the branch? Then branch is 0. How about the mem to read? Load instruction needs to access data memory for read. So mem to read should be 1. How about the mem to read? So for this multiplexer, we select this path. So we select the output from the data memory. So this should be 1. ALOP was 0, 0. And the memory write is 0 because it's load instruction. So memory write is not required. How about the ALU source? Oh, this path is selected. So which means that the ALU received data, one data from immediate data. So ALU source is 1. How about the leg write? What happened? Okay, so leg for the load instruction, so load instruction needs to write data to registers. So reg write should be 1. Okay, so 1 is unexpected operation. Okay, how about the BQ? This is the branch instruction. So this OP code is, so we can check the RISC-V instruction set here. So for the branch instruction, the OP code field is the 11000011. Okay, so 11000011. So which means that the OP code field are 11000011, or this is the branch instruction. So branch is 1, which means that it becomes the 1. So which means the output of this AND gate is determined by this signal. So true and false of the branch condition. Okay. So if the branch, our processor just support the BEQ. So and then for the BQ, we just performs the A minus B equal then. So if A minus B equal 0, which means, this is the A and B are equal each other. So 0 becomes the 1 for this case. So this output of this AND gate becomes the 1. And then if the output of this AND gate is 1, then the PC, next PC is a PC underbar next is selected with this path. Okay. So BQ is the branch instruction. So which means that branch becomes the 1 for the branch instruction. And how about the mem to read? It's a 0. Mem to rec. Actually, any value is okay. Actually, so don't care, because if we see this multiplexer, and then if you see the path, the input of this multiplexer, then we can find that the color of this wire is gray, not black. So which means that actually the branch instruction does not require data from memory nor the result from ALU. So actually, for this case, we can set any values for this mem to rec control signal, because these two paths are not activated. Okay. Now how about the ALUP? Is should be 0, 1, is because it's the branch instruction. How about the mem write? It's 0. Okay. How about the ALU source? It's 0 because ALU need to compare two data from register file, like read data 1 and read data 2. So ALU source is to be 0. How about the reg write? Yeah, right, it's a 0. The branch instruction just change PC. Okay. So, if we just know how instructions are executed in the processor, then we can easily determine the control signals. Okay. Right. Okay. So no. Branch cannot do big. So you mean actually branch instruction cannot use immediate value. Okay. So actually BQX1, 3 is not possible. It's not possible. Okay. So branch instruction just compare two data from registers. So two register data. Okay. So we can build a single cycle processor like this. So first we define how each data path element work for the single cycle processor. And then we connect the input and output ports of data path elements. So we first build the data path of single cycle processor. And then, these data path elements have control port that we need to control the behavior of these different data path elements. So single cycle processor also requires control unit. And then, we can generate the control signals based on the instructions. So which means that the control unit generate the various control signals, and then we can connect these control signals to the control port of data path element. That's it. So which means that we can build single cycle processor that can execute RISC-V instructions. Okay, do you understand? So okay, so we can build this RISC-V processor. Oh, it's very good. But what's the problem? The problem is that okay, I cannot use that slide. What happened? So problem is that our real hardware has delays. So which means, so these instructions, so one instruction should be completed within one cycle. That is the definition of a single cycle processor. So single cycle processor means that every instruction is completed within one clock cycle. Then, which means the clock cycle, the clock period is determined by critical delay of data pass in this single cycle processor. So what does that mean? Actually, these are real hardware. So, and then real hardware has delays, which means that if the input is given to this data pass element, after some delay, the output is generated. So, which means that instruction memory has delay, register file has delay, also every box has delays. Also, ALU has delay, data memory has delay. Then, every instruction need to access these data path elements. So which means that in order to execute these instructions, the instructions will be completed after delay of this instruction memory plus delay of the register file and the delay of the ALU and the delay of the data memory. Especially for the load instruction, the load instruction need to access instruction memory, register file, ALU, and then data memory. So which means that the delay of these data path element actually included in the box should be accumulated for calculating the total delay of the load instruction. Okay, and then the clock period of this single cycle processor should be longer than this delay of the load instruction. Okay, this is the longest delay of for executing an instruction in this single cycle processor. So which means that the clock period should be longer than the delay of load instruction. If we so in the chapter 1, we learned that execution time is instruction count, CPI, T. But T will be very low for the single cycle processor. It's not good for performance. Okay. This period, clock period is very long, then our computer will be very slow. Everyone does not like our processor. Okay. So that's very critical issue for the hardware architecture. So we need to find a way for improving performance. So we will learn about the pipelining next class, and then with the pipelining, we can improve the performance of our processor. And it's also very important topic of this course. Actually, the pipelining is a very important concept in digital system design. Okay, but you need to remember that with a single cycle processor, the T is very long. I think the clock period is very long, so it's not good for the performance. Okay. Okay. So I stop here. So yeah. Okay. So we will take the midterm exam on May 2nd, right? So Monday, May 2nd. So actually, so in the next class, where is so I believe I can cover until people. Okay. So So in the next class, I plan to cover until the page number 19 of this chapter 5. Actually, it's a chapter 4 of the textbook, but I split the single cycle processor and the pipeline processor for the chapter 4. So I assume that the midterm will cover until the page number 19 of the chapter 5. Okay. Okay. Any questions? Okay. Thank you for your attention. Then see you in the next class.